Welcome back to the last section that we're going to do this semester, and that's talking about oscillations and waves. We had a test yesterday. A lot of people finished early, which made me feel good. That indicated that they must have had a good handle on the material. I haven't got them graded yet. I'll be working on that today and tomorrow. Yes?
What about the lab test?
I have not checked to see if he has them graded. He probably does, but I have not checked. So as soon as I have the test graded, I will make sure that all grades are up to date so you know exactly where you stand. Because I know that's important to everybody. I mean, you'd be silly if it wasn't. Excellent. That's called coordination. Excellent. Well, I guess I won't be using this today. Yeah. I don't know where the tip is, but it ain't there anymore. So, no drawing. This is going to be tough.
Use my pen if you want.
Yeah, that would be good. Because I wanted to do problems and stuff. Now the question is, will it write or do you have to do some pairing? No, it writes good. Excellent. Yeah. Hey, you got the $100 pin too. I really appreciate it. Remind me to give it back to you. And I'll try to be really careful. I do have extra tips that I bought because this is the second time I dropped it. Okay, so I didn't even write on here what we have in the past because we're really changing topics quite a bit. We're talking about oscillations. Now we're going to start with periodic motion. If something is periodic, it's pretty simple. I don't have to sit here and ask you what a periodic means. Periodic means it repeats over and over and over. Now, the period is the name we give to the time that it takes for it to repeat. So, something I might talk about is going to church. The period for my church attendance is once every 7 days. So, the period is the time between those 7 days. So, period is the time between things. Other common periods. What's the period for, let's take one that you will know, for the Earth to orbit the Sun? I almost said the Sun to go around here. What's the period for the Earth to orbit the Sun? 365.2422 days. Something you may not realize. Why do we have leap year?
To count another 0.22 something, whatever.
Because 365 is not 365.2422. So back in the ancient days, Julius Caesar came up with a calendar that added a leap year every 4 years. And so if people talk about the Julian calendar, they're talking about a calendar that every 4 years you throw in an extra day, which we call a leap day. But then, how long would a day be on the Julian calendar? Or a day. How long would a year be on the Julian calendar? Notice I said would. We don't use the Julian calendar, if you didn't know that.
366 days.
Would be 365 and a quarter because you're adding 1 day each 4 years. So you're adding a quarter day each year on average. But that's not 365.2422. And so the Gregorian calendar is what we use today. The Gregorian calendar, every year that's divisible by 100, you skip a leap year. And so that would make the average day 365.24 days long. But now that's too short. And so every year that's divisible by 400, you add in a leap day. And so that makes the average year 365.2425 days long. And they figure that's close enough to correct. Why is that important? Because the calendar shifts and you can't use the calendar for things like New Year's. In fact, how many New Year's days technically do we have? 3. We have Christmas Day. That's supposed to be New Year's. We have the winter solstice. That's supposed to be New Year's. And we have the day on the calendar that's marked as New Year's. Why are they different? Because the calendars drifted over time. And so if somebody said, we're going to call this the New Year, and then sometime later, we're going to call this New Year, that's how they end up different times. Now that we're on the Gregorian calendar, it will shift by no more than a day. Okay, so period. the time between something repeating. Frequency is how often something repeats. So if I have a period for my church attendance that's 7 days, how often do I attend church? Once every 7 days. Same days.
Once per period.
Once per period. So frequency is simply 1 divided by the period. Now, what is our SI unit for period? It's time, so what's the SI unit for period? Seconds. So period has units of seconds. Frequency is 1 over the period. So what are the units of the frequency going to be? 1 over seconds, which we call a hertz. So hertz means 1 over seconds. It's not something special. It's just like Newton means kilogram meter per second squared. So you can use, in this case, 1 over seconds or hertz interchangeably, just like you could use newtons or kilogram meters per second squared interchangeably. Then we have angular frequency. Angular frequency is a slightly different beast. I'm going to show a demonstration with that wheel in a little bit where you'll see where it comes from, but angular frequency is measured in units of angle per second instead of per second. Now, of course, what's the unit for angle? I have a charged question here. There isn't any, but we call it a radian because there's 2 pi radians in a complete cycle. Oftentimes people, instead of putting frequency in 1 over seconds, they'll say cycles per second. And then it makes it easier to understand where the angular frequency comes from because you have 2 pi radians in 1 cycle. And so the angular frequency, we use the symbol omega, is 2 pi times the frequency. So when you've gone through 1 period, you've gone through an angle of 2 pi radians. Now you could also put it in degrees if you wanted. I don't know that I've ever seen it done in degrees, but you could put, 360 degrees times F and have it in degrees per second. And surely somewhere down the line, you'll probably have a problem that throws in some crazy angle, just like I'm sure you all appreciated on the test, all the Fahrenheit I put in there. I just wanted to make sure that you were, yes, we have to shift this to the correct unit. Okay, now we're going to talk about linear restoring force, spring systems, and pendula today. Notice the plural of pendulum is pendula. I am in an educating mood today. Union College put out an announcement that this building was named after Mrs. Kruger. I can't remember her first name. She died about a year ago. And they said that she was a Union College alumnus.
What does that mean? What's an alumnus?
Alumnus means a male graduate. I actually was rather concerned that we look ignorant to the masses and using the wrong gender term. And so I pointed it out to the PR people. They said, well, Union College has decided that for Union College, alumnus is gender neutral. Because apparently Union College has control of the English language. So what is the feminine singular? Since many of you will someday be, good answer, alumna. When you graduate, you will be an alumna of Union College. Now, let's say 2 of you graduated and you're both men. Then collectively, you're alumni. That is plural masculine. But what if we talk about this table? You've all graduated. You are not alumni of Union College. What are you?
It's AE.
Yes, AE, right. Just these kinds of things. I felt that you needed an education on that. It's not physics.
Don't you know only men graduate from Union College?
That is incorrect, ma'am.
In Pennsylvania, we use alumnus for everybody.
Yes, we're a little ahead of the curve on this whole gender identity thing, apparently. So staying on topic, or moving back to on topic, period, there are equations to relate and the symbols we use. We use a capital T for period. Period is 1 over frequency, or 2 pi over omega. Frequency we use is F. If you go to higher physics, we'll use the letter nu, a Greek letter that looks kind of like a V. But for you guys, we stick with F, is 1 over period, or omega over 2 pi. And of course, angular frequency is 2 pi F, or 2 pi over period. I pointed these out. I put 3 different equations. Obviously, this is one equation. Just solve for a different variable each time. Just want people to be familiar with the variables and what they mean. Now, I want to look at examples of oscillatory motion. So the first thing I have here is my rotating platform with a cup with a mass on it. I put the cup so it would have more friction than mass. We've got that stick sticking up. So as I make this go in a circle, if you just look at the aspect like this, it's repeating, right? It's going to come to this position over and over again. And the time it takes to do one cycle, what do we call that?
Period.
The period. And if we take 1 over the period, we have the frequency. But we can also talk about the rotation per unit time. And what would we call that? Right. So you can see all 3 of those interrelating. Now, if you just talk about the back and forth motion that you see, since it's going in a circle, so we have our cup going around the circle like this. And if we're only going to talk about the aspect that's on the x-axis here, then when it's at some angle of omega t, what's the x component at that point? So it has radius. Let's put capital R there. Capital R to make David, feel uncomfortable. We had a conversation.
We did.
What's the x component of its position here? R cosine, and the angle is omega t. And what's the y component?
R sine.
And so as time passes, its x component is changing sinusoidally, and its y component is changing sinusoidally. Now I put both x and y components on there because sine is the one we actually choose to make the analogy with. And so we say that we have simple harmonic motion. It's a new name, simple harmonic, not just oscillatory motion, if we just look at the y component of its position. And so we're going to use this as an analogy as we go through, but simple harmonic motion is defined as motion where you have a sinusoidal motion. So where your position follows this equation. So this picture here, what it's showing is if I have another kind of oscillator, a spring, I put a mass on the spring, and I have it oscillate up and down. If I were to plot the position as a function of time, that's what this picture is showing, it plots out a sine wave. Now, how many people are intimately familiar with a sine wave? That's only a couple.
Let's just say it's not a cosine wave.
Okay, when we say a sine wave, we mean that it's sinusoidal, so a cosine wave and a sine wave both fit that. Because that's an important question. So let's just make sure that we understand what a sine wave looks like. So if I make an axis here and I have time on this axis and I have displacement. Displacement is a new word in centimeters. Displacement is the distance from its equilibrium position to its actual location. So here's the equilibrium position. If I take this and I lower it 5 centimeters, then its displacement is minus 5 centimeters because I lowered it. Consider that positive. Now if I let it go, you see the displacement is going positive, negative, positive, negative. So if I make a graph like that, it's going to look something like, now this looks like a straight line here, and that's just because I wasn't careful enough. That's as good as I can get because I'm not a pro at drawing. A sine wave starts at 0 at time equals 0 and goes up. So that makes it a sine wave. But a cosine wave, if I had started with time equals 0 here, so it starts at maximum, that would have made it a cosine wave. So you can see they're the same thing. It's just when time equals 0 that's different. So that's why we, as a group, they're sinusoids. It's the same shape. Cosine means that at time equals 0, you're at maximum. Sine means at time equals 0, you're at 0 going up. On this graph, could you tell me what the period is? If I had numbers along the axis, let's say, okay, get rid of the cosine wave stuff.
Period would be 2, 5.
Let's say that this is 0, 1, 2, 3, 4, 5. Okay, we have 4 is what somebody said for the period, and that's correct. Why is 4 the correct value for the period?
One full cycle.
One full cycle. Now, one thing that people sometimes think is, well, shouldn't 2 be the period because it started at 0 and it came back to 0? But it's not the same because it started going up and now it's going down. And so that's, well, in this case, that's half the period. So the period is the time to repeat. So the period would be going from here to here. Or I could have made the period going from 1 to 5, right? Because that's also repeating. Or I could have chosen some bizarre place like here and gone to that same place here and had the period like that as well, if that's what floats my boat. So the period is the time it takes to repeat. And so if the period is equal to 4 seconds, then what's the frequency? 1/4, and I'm going to put 1/4 with units of hertz, just so we remember that hertz means 1/seconds. What about the angular frequency? And what are those units? Not hertz. They're radians per second. What radian is unitless. Remember I asked that question, I said it's a trick question. Radians are unitless, but this tells us it's not hertz, even though it's still technically 1/seconds.
Could you hypothetically call it radial hertz? You're asking a question.
I've never heard that, so I'm going to go with no. I hypothetically, you can call whatever. You can call them Joes. What, you know, it's your call.
I mean, T is for period, so.
So that's how we can read from a graph what these things are. Now, I have, oh boy, I didn't start woo clap, so you can go there as I'm going there. Thank you. Come on.
Why is T for period?
Time.
All the way up. I'm calling back on the other side now.
Woo clap, which is probably going to make me log in. I knew I forgot something before class. This was it. Come on, baby. All right. So we have 5 people who got logged in while I was going there. Maybe. Depends on which button it is. That wasn't it. There. What was happening was me going the wrong place. Oh, yes, because I have it showing up live on the computer. Right, not anything because we're back to no question. Okay, 10 people are in. That's all but 2. 11. 1 to go. Still waiting on one person. Somebody needs some help?
How did you know?
We are almost there, right? Hey,
Over there.
says the one wearing the earbud. All right. Of course I saw that. You've been wearing it all class. Okay, so our first question, match each unit with the property that has that unit. Now, you may not get 100% on this because you'll notice there's frequency on here twice, and if you match to the wrong one, it'll say you're wrong.
That's just second.
I don't know what you mean by that. Just a second.
Number 5.
Yes.
Yes, that's second. Yes. Okay.
No.
Apparently, you figured out how to answer because I didn't have a way to test how you answer this.
There's like drop downs for each dog.
This one?
There's just like drop downs for each dog.
Oh, okay. All right. 1/3 complete. It's what I do when I'm in the gym. I'm going for 41 minutes. And I'm calculating what percentage I'm done every. We are 75% done now. No. Well, 2 people didn't answer. I'll just move on. Except for I didn't mean to do that. I meant to do this. So 10 people, all people said meters per second is speed. And all 10 people said angular frequency is rads per second. Good job. All but one person said period was in units of seconds. Not sure what else would have been there. And then we have these here. If you add them up, we have only one mistake among the frequency answers. Right? You can't tell which is which, but you just add them up. Because hertz and 1/seconds are both frequency. So, just the one thing to remember, seconds is the measurement for period. All right. Example. This here is an example of a simple harmonic oscillator. It goes up and down. Now, for a simple harmonic oscillator, what did I say previously was important about a simple harmonic oscillator? The motion is sinusoidal. Well, it turns out, and this is so quick and easy to prove with calculus, and such a pain without calculus, that if you have the net force is minus a constant times how much it's displaced from equilibrium, that gives you sinusoidal motion. Now, we call this simple harmonic oscillation. You can see it up there. So that equation I put in the box is the requisite condition for something to be a simple harmonic oscillator. So if you look at that force vector, net force vector, equals minus. What is the minus going to do to direction? It's going to change the direction to the opposite direction. So the net force is in the opposite direction of k times x vector. So that means with this system here it's in equilibrium. So we set x equals 0 at the equilibrium position. If I pull down, the net force, according to that equation, should be going what direction? My displacement is down, so what direction should the net force be? Up, because it needs to be the opposite direction. So the net force is up, so when I let go, it comes up. We call that a restoring force. So rule number 1 is you must have a restoring force, a force that's going to bring it back to the equilibrium position. Rule number 2 is, notice that is minus k times x. K is a constant, x is linear, so it needs to be a linear restoring force. So if you were to look back at the first slide, I had these two words as two separate lines for simple harmonic oscillation. It needs to have a linear restoring force. An example of something with linear restoring force is a spring, because the equation for the force of spring is force equals minus kx. So the spring is your classic example of a simple harmonic oscillator. Now, before we move on, I want to just do some measurements. So who has, everybody does probably, who has a simple timing device, i.e. stopwatch on your phone or watch? Okay.
It really is.
So I'm going to ask, who wants to be our official timer? Okay, Andy's our official timer. So I'm going to have you, Andy, time how long it takes to do 10 cycles.
Okay.
So I'll say start, I'll say stop. Okay? We're doing 10. Why would we do 10 and not one cycle? Yeah, we will have a more precise answer. So start. 1, 2, 3, 4, 5, 6, 7, 8, 9. Stop. Okay, so what do we have for that?
10.29 seconds.
You said 10.29? So I divided that by 10 to get 1.029 seconds. Now our condition here was I had 200 grams and I pulled it down, what, about 5 centimeters? Now the maximum displacement we have a name for. The maximum displacement is called the amplitude. A number of vocabulary words because we're starting a completely new topic. So we had frequency, period, angular frequency, displacement. The displacement is the distance from equilibrium to where it is. Amplitude, the maximum displacement, the maximum. Now I'm going to do this again. Instead of going down 5, well, I'll take it up. I'll take it up about 10 centimeters. So I'm doubling the amplitude. So you ready?
Time.
Yeah.
1 second. I'm ready.
Okay. So, wow. Did you start ready?
I'm ready.
Okay. Do that again. So I take it up about 10 centimeters. Ready? Start. 1, 2, 3, 4, 5, 6, 7, 8, 9. Stop.
10.27.
So what happened to the period when we doubled the amplitude? It fundamentally didn't change. So it seems kind of nonsensical because it had to go twice the distance, and yet it had the same time. But remember, if you're at twice the displacement, the force is twice as big, the acceleration is twice as big, and so it's going a lot faster. So even though it's going a longer distance, it's going along faster. It turns out that the period is independent of the amplitude. Now I'm going to change it from 200 grams to 500 grams. And now we'll only do one displacement because we've shown that it's independent of displacement. What I'm going to do is bring it over here and hopefully get it so it's hanging out over the edge. No. It's definitely hit the edge. Well, we will have small amplitude. So I'm just going to bring it down to here. So you ready? Okay, so we'll start at the top this time. Start. 1, 2, 3, 4, 5, 6, 7, 8, 9.
Button on my watch.
Yeah,
So
I figured from most sounds that something is done wrong. Okay, so we'll just do it again. You ready? Okay. Start. 1, 2, 3, 4, 5, 6, 7, 8, 9. Stop.
15.03.
Okay, so when we change and I just put the mass now because we determined the amplitude doesn't matter. When we change to a larger mass, what happened to the period? It increased. But note that we more than doubled the mass. Did the period more than double? No. Did it double? No, it did less than double. So it's not linear with the mass. So we've seen that the period depends on the mass, but not on the amplitude. There are other things it depends on, like the spring. So if I take this spring, I put 200 grams on it, I don't think it'll damage it. Going back to the 200 grams with a different spring, notice the spring stretches a lot more. And so one last time, you ready?
I am actually ready.
Okay. Start. 1, 2, 3, 4, 5, 6, 7, 8, 9. Stop.
14.93.
So we see that if we compare the same masses but different springs, we had a different result as well. Now, one thing that we learned a long time ago, and we just went over real fast, is the spring constant. The spring constant is a measurement of how much K is, how much it stretches when you put a mass on it. So right now, well, let's just get a meter stick. Right now, the loop on the spring is, say, 46.25 centimeters from the desktop. If I take the mass off, then it goes to 97.5. So the difference in those two, 97.5 minus, what did I say?
46.25.
So,
51, just about.
what's my uncertainty in these measurements? Because you always need uncertainty.
Would the uncertainty be in the measurement of time, or?
Well, this was just measuring distance. At best, I'd say 0.2 centimeters because I was eyeballing it. So this one here, I'm going to round to 3 because of that uncertainty. And so the difference in those two is 50, not 40. 51.2 centimeters is delta X. And the force that I hung on there was 0.200 kilograms times G, 9.80 meters per second squared. So that's 1.96 newtons. Convert these to SI units. And so the spring constant is equal to the force over the amount it was stretched, which would be 1.96 over 0.512 meters. The spring constant has units of newtons per meter. And when you do that, it's going to be somewhere in the ballpark of, let's say, 3.9. Right, you can put it in the calculator. It's not important to have exactly the right number for demonstration purposes. For homework purposes, of course, you want to get the right number so you get the right points. So that's how we calculate the spring constant, and you see its value has units of newtons per meter. Now, if I had changed to this one, we won't repeat the measurements and calculate spring constant, but you can see that with the same mass, it does not stretch 50 centimeters. It stretches more like 15 centimeters. And so its spring constant is going to be like 3 times bigger. Understand the spring constant idea? All right. Back to this. I said with calculus, it's easy to show. With calculus, we can show pretty simply that the angular frequency that it will oscillate at is the square root of K over M. So I can take my situations that I did before with the same spring constant, but a different M. So these top 3 were with the same spring constant, right? This one here has omega is equal to square root of K over 0.200 kilograms. And this one had omega equals square root of K over 0.500 kilograms. So if I take these, the ratio of my frequencies, my angular frequencies here, should be equal to the square root of 0.500 over 0.200, or to make life easier for everyone, that can't be square root of 5, 2.5. Square root of 2.5. So let's just compare and see if we're correct. What is the square root of 2.5? 1.58. Okay. Yeah, 1.58 will be good enough. Now, if we take our actual numbers, omega over omega prime should be equal to 2 pi over period, right? Because omega is 2 pi f. And so it's 2 pi over period. Yeah, that's right. And I think it was 1.50, but I got 1.503 over 1.028. If you calculate these, it's not going to come out to be exactly 1.58 because it's a little less than 1.5. What does that mean? It means we're probably off a little bit in our period measurements. But you can see that it was following what it's supposed to do. It increased the period when I increase the mass, but in a value that's proportional to the square root of the mass. So this is another important thing to be able to use. The angular frequency omega is equal to square root k over n. So that's one kind of simple harmonic oscillator. Another type of simple harmonic oscillator, here's the equations, right? Newton's second law says net force is minus kx if it's simple harmonic oscillator, and ma because of Newton's second law. And then using calculus, that's equal to m d second x dt squared. And you then solve that equation. That's how you get that omega is equal to square root k over n. Simple pendulum is another example of a simple harmonic oscillator. So I have a simple pendulum here, and we're going to make measurements again, just like we did before. So I'm going to maybe get this untangled. Hang this on here, and we'll swing it back and forth, and we'll measure its period as it swings back and forth. So I'm going to start with the small amplitude. You ready? Start. 1, 2, 3, 4, 5, 6, 7, 8, 9. Stop.
17.74.
Okay, now I'm going to go to large amplitude, because that was the first thing we tested before. So I'm going to bring it up here like 45 degrees. Start. 1, 2, 3, 4, 5, 6, 7, 8, 9. Stop.
18.25.
Do you think Andy's bad? Those are not the same, are they?
Shouldn't they be though? Or awfully close?
No. Because this is not a simple harmonic oscillator. Why is it not a simple harmonic oscillator? What's the rule for something to be a simple harmonic oscillator?
We don't have to have a sine wave or a cosine wave.
Okay, it does have to have a sinusoidal relationship, but we have the rule that it has to have restoring, so that minus sign, proportional to displacement, a linearly proportional restoring force. Now, if we look at the pendulum, does it have a restoring force? Does it have a force that brings it back toward equilibrium? Gravity does. But it's just a portion of the force of gravity, right? When it's here, gravity's pointing straight down, it's not restoring. When it's out here, part of gravity is pulling in the direction it can move. And so that's going to be, the force is mg sine theta that's pulling it to restore. When it gets up here, it has, all of mg restoring. So the force is restoring, but that restoring force is force restoring is equal to minus mg sine theta. Sine theta is not linear. And so it's not a simple harmonic oscillator unless, because that, of course, I don't have a direction here for, it's hard to define the direction for the motion. I mean, you can put theta hat, but then everyone's going to be more confused. So it's just restoring. For small angles, sine of theta is equal to theta minus theta cubed over 3 factorial plus ... You can make a Maclaurin expansion. I think that's Maclaurin. Taylor and Maclaurin, the only difference is about 0 or about wherever you want. of sine theta about 0. And for small angles, like if theta is, let's say, 1/100th, then theta cubed is 1/1,000,000th. So 1/100th minus 1/1,000,000th over 3, you can throw away that 1/1,000,000th over 3. It's meaningless. And so for small angles, all of these terms that are higher than the first one are approximately 0. And so for small angles, sine theta is approximately equal to theta. So then my force restoring is equal to minus mg theta. Well, theta is equal to the arc length, oops, my finger hit a button, the arc length over the radius, so the length of the string. And now we have something that's restoring and linear with respect to how far it's swung out. So if you have a small angle, then a simple pendulum means you have a point mass hanging from a massless string. We're in general physics, everything is simple. Complex pendulum or a physical pendulum, my leg's a physical pendulum. I have mass distributed throughout it. It behaves differently. So for a simple pendulum, it's a simple harmonic oscillator if you have a small angle. Now, of course, what's the definition of a small angle?
Less than 1.
Less than 1 what?
Less than
Okay, we have radian, we have degree. If you want to be real technical, small angle means sine theta equals theta to within how much you're allowed to be off in error. So if you want to be really precise, then it's going to have to be really small angle. If you want to be pretty close, 15 degrees is close enough to a small angle. So it depends on what your ruling is for how precise you have to be. But it has to be a small angle. If you have it's swinging at 45 degrees, that's never going to qualify as a small angle, as you could see from Andy's measurements. And I have good faith in Andy's measurements because you saw she was only different by, after we divided by 10, 2 parts in 1,000 on our measurements we did before. Oh yeah, she's proud. So what's the condition for a simple pendulum to be a simple harmonic oscillator? Small angle. And for the small angle, what is K? Just looking at this equation, remember our rule is we have to have force net equals minus K. I'll put S here because S is what we use for position. So what is K? Which in this equation that we worked out? Well, no, the negative was here, so. Mg over L, that's what K is. But then since omega was the square root of K over M, that means it's the square root of Mg over L divided by M. Those M's conveniently cancel, and it's equal to square root of G over L. So it doesn't matter what mass I have hanging from the pendulum. That's not going to affect its period. All that affects its period is G, the acceleration of gravity, and L, the length of the pendulum. So one of the experiments I did when I was in college for physics lab was to measure what G is by varying the length of the pendulum and calculating and measuring the angular frequency. Okay, another woo clap. Look, it says for syllabus. You can tell where I copied this slide from. I didn't notice that until now. So our next question, under what condition is a simple pendulum a simple harmonic oscillator? Yeah, only one. I have 2 messages, which I'm not going to click on because you saw what happened when I went to that last time. Never got back. I'm going to have to give this more time. We only got 4 people in. 1/3, 5/12. What was the button to restart it? I forgot what the button to restart is. Well, that's great. We don't use this enough. All right, well, I guess we won't restart it because I can't figure out what the restart button is. It was really simple. So we had 3 people that said small amplitude. Those 3 were correct. One person said short length. Nope, length doesn't matter. You'll change the period. The longer the period, the higher, or the longer the length, the higher the period, but it won't change it as far as simple harmonic oscillator. Likewise, small mass. Nope, any mass. It's only the length that matters. Okay, we won't have time to do the example problem. We will convene again on Friday and continue on with simple harmonic oscillators. And soon get into sound, which is, of course, probably the most fun topic of the semester.